Assalamu alaikum students. So we are going in for week lecture number 8, in which we will discuss about energetics of alpha decay in detail, and what kind of energy for outgoing particle is important and how we can calculate it. So uh, alpha particles were first identified as the least penetrating of the radiations emitted by naturally occurring materials. So it has very less penetrating power. In 1903, Rutherford measured their charge to mass ratio by deflecting alpha particles from the decay of radium in electric and magnetic fields. Despite the difficulty of these early experiments, Rutherford's results was only about 25% higher than the present accepted value. In 1909, that he showed that, as suspected, the alpha particles were in fact helium nuclei. In his experiments, the particles entered and evacuated thin wall chamber by penetrating its wall, and after several days of collecting, atomic spectroscopy revealed the presence of helium gas inside this chamber. It means they were actually alpha particles, helium, which are the nuclei of helium atom. So these helium many heavy nuclei, especially those of naturally occurring radioactive series, decay through alpha emission normally or usually. So alpha decay is a type of radioactive decay in which the atomic nuclei emits alpha particles, which we already see that these are helium nucleus, and therefore transforms or decays into different nucleus, which is the daughter nucleus, and the daughter nucleus have a mass number reduced by 4, means A will be reduced by 4, and atomic number Z is reduced by 2, because in helium we have two protons and 2 neutrons, so n the neutron number will be also reduced by 2. So an alpha particle is identical to the nucleus of helium atom. So it has a charge of 2 plus due to 2 protons and a mass of 4 amu. So for example, uranium 230 decays to thorium 234, the alpha particle will be emitted, and it has a change in the mass number about to 4. So in the equation below, where we have presented X as a pinnet nucleus, which convert to Y daughter nucleus, and alpha particle is emitted. So X is a heavy nucleus which converts into daughter nucleus, which also is heavy, and alpha particles is light as compared to Y. So the Q value or the emitted energy will be shared by Y daughter nucleus and He helium nuclei. Due to the lightness of helium atom, the most of the energy will be carried by the helium atom, helium nuclei, and it's about 98% or 99%. So the X is just converted into the Y within the sample radioactive sample, and we can detect the alpha decay by detecting the alpha particles from it by using some detector. So the most important thing in alpha decay is to find out the energy of the alpha particle. So in the next slides we will find out how we can find the calculate the energy of the alpha particle. So alpha emission is a Coulomb repulsion effect. Actually, we will also discuss the theory in which the alpha particle is already formed within the parent nuclei and wants to come out of the parent nuclei, but it has some less energy, and then there is some Coulomb quantum tunneling effect, and we can see this alpha emission to quantum tunneling. So it's basically Coulomb repulsion effect. So it becomes increasingly important for heavy nuclei because the disruptive Coulomb force increases with size. Because if you have a bigger nucleus, we have more number of protons, and we have more charge, and we have more repulsive Coulomb force, and it's more possible that we will end up with alpha decay. So nuclei with a mass number greater than 210 are so large that the short-range nuclear forces barely balance the mutual repulsion of the protons, and the alpha decay occurs in such nuclei. By reducing their size, they become stable, and strong nuclear forces becomes dominant, and by reducing their size by the emission of the alpha particle, they reduce their size and increase the stability of the resulting nucleus, such as the daughter nucleus. So this is the example of the alpha decay. Uranium 238 is decaying into thorium 234 with the emission of helium particle. So here's the calculation of the alpha decay process. In the equation 1 is the X is going to decay in X prime, the daughter nucleus, with emission of alpha, and we assume that the initial decaying nucleus X is at rest. Therefore, its kinetic energy Tx will be 0. So according to conservation of energy in this alpha decay process, on the left hand side, initial energy must be equal to the final total energy on the right hand side. So on the left side we have only X, so which is at rest, so its kinetic energy will be 0. We have only its rest mass energy, which is equal to mx c square. On the right hand side, so we have two products, X prime and alpha. For X prime we have rest mass energy and also the kinetic energy Tx prime, and for alpha we have the rest mass energy and the kinetic energy T alpha. And for us, as we already know, due to the lightness of the alpha particle, we have to determine the T alpha. By just simple mathematics, we can write the equation number 2, which is actually the Q value of this alpha decay. So Q value will be equal to the initial mass minus the final mass, and this decay will occur spontaneously if Q is greater than 0. We don't need any threshold energy. So from this equation number 2, we can also write Q value in the form of the kinetic energies, such as Q is equal to Tx prime plus T alpha. By using the conservation of the linear momentum, we can write the initial momentum is 0 because the X is at rest, and the final momentum will be of P of alpha particle P alpha, and the daughter nucleus momentum Px prime, and in magnitude these two momentum will be equal, which means that the X prime daughter nucleus and the alpha helium nucleus will move in opposite direction after the decay process. So by using equation 5 and 4 and using the relation between the kinetic energy and momentum, T is equal to P square over 2m, and by using some calculation as shown in the figure, we end up with equation number 6 by simplification. So this equation number 6 will tell you about the kinetic energy of the alpha particle, which is equal to q over 1 plus m alpha over mx prime, which means that T alpha kinetic energy of the alpha particle is not exactly equal to q, but it will be less than q, because in the denominator we have m alpha over mx prime, and this is some number which is adding in 1, so we have T alpha less than q. So this m alpha over mx prime can be converted into a's, just as m alpha over mx prime is equal to 4 over a minus 4, and a is much greater than 4 for daughter nucleus. So by writing this in equation number 6, m alpha over mx prime, by converting into a, 4 over a minus 4, we end up with equation number 7. So by just finding the a number of the daughter nucleus, we can find the kinetic energy of the alpha particle, which is about 98% of the Q volume, and just 2% of the remaining will be carried by X prime daughter nucleus. Thank you, students, for this talk, and goodbye.